Welcome to Mr. Frolic's physics classes. In this video, we will see an introduction to measurements.
Hello there. In today's lecture, we'll talk about measurements. And I have a question for you. What it is to measure something? Yes, Mark?
Mr. Frolic, is it to determine the length in centimeters of an object?
Quite right. You got it quite right. You see, to measure something, it is to compare what I want to find the relative size against a standard. If it is in length, my standard is going to be a meter. If it is a mass, my standard is going to be perhaps a kilogram. So I will just compare and see how many times either what I want to find, what I want to measure is bigger than my standard, or how many times what I want to measure goes into my standard. So, as a first example, I would like you to take a measurement of the object represented in the slide. Let's assume that this is a normal meter stick and that is graduated in centimeters. But I want it to be as precise as possible, but still keep common sense. Let's see what you get.
Mr. Frolic, I got 12.2 centimeters.
I got 12.4.
Well, I think it is 12.25 centimeters.
I think it is 12.5 centimeters.
So I've listed here the results that you all got me, but I want to offer my own result in here. I would say that my result is 11.5. So I have 12.2, 12.4, 12.25, 12.5, 11.5 centimeters. Let's look at these results here, and I'm going to ask you, which of these 5 results is correct, is the right one? Maybe, instead of asking which one is the right one, we should ask which one is wrong, which one is clearly not it. Yes, you got it right. 11.5 is clearly off, because we know for a fact, when we look at this object, that it is slightly more than 12, less than 13, between 12 and 13. The 4 results that you guys had for me are within that range. But mine, the 11.5, is clearly off. Now I want you to consider the second example, the meter stick and the object being measured on this slide. Please, take a reading, again, being as precise as possible, but keeping common sense.
Mr. Frolic, I believe the length is 12.85 centimeters.
Well, my answer is 12.847 centimeters.
I believe the best measurement is 12.83 centimeters.
I agree with DJ. The best way to express the measurement is 12.85 centimeters.
Okay, so now I got your results in here. And we have 12.85, 12.83, 12.847, and 12.85. I'm not going to offer any result now. Apparently, I'm no good at this. But if we see our measurement now, we have in here, we know that it's more than 12.8 and less than 12.9. And then we are just estimating a little bit. Now, a question I have is, can we really read 847, divide this here in this small interval in 100 parts and then visualize 47 out of it? It's kind of hard. Another thing I would like you to consider is this. When my meter stick became more precise, our results automatically converge to a narrower range of readings. Okay? When I knew I was between 12 and 13, we had a bigger variation from 12.2 to 12.5. Now, they're all within a small range of 12.80 something. You see that when we measure an object, we always end up with a certain portion that we know, we believe we know, is more, we have more certainty, and a tiny little bit that we estimate, that we guess. And then there are two things here to consider. The first thing is this. On the first example, if I don't really know whether this is 12.2, 12.3, maybe even 12.4, I don't really know exactly what comes after the 12, does it make sense going another decimal place and writing 12.25 if it could really be just 12.3 or 12.4? On the second example, I know it's between 12.8 and 12.9. But I'm not sure if it's 12.83 or 12.85. That's a guess. So does it make sense writing another digit and trying to go to 12.847? Another thing to consider is, right now, I see my meter stick and I see the readings. But when I'm writing a paper and I want to report this, to publish, my readers are not going to be seeing those pictures. And I need to be able to convey, as I write my results, some information about the precision of my meter stick. So let's make the following agreement in here. That for every measurement we will have, every measure we make, we will include only one estimated digit. Okay? So let's make this deal. We will always take our readings including just one estimated digit. I'm going to ask you now to consider the next example that is on the slide. Please take a reading of this one. Let's see what we get. This example is the meter stick itself. It is the very same one of the first example. But the object I'm measuring now is not falling between 12 and 13. It apparently falls exactly at 13. So I think that you all would agree with me that I should write 13. But remember our agreement to writing just one estimated digit. So if I write 13 this way, I would actually convey that I am more certain about the 10, but I don't know about the 3, that I know is more than 10 and less than 15 or 20. So a meter stick that will produce a reading of 13 would be, for example, something like this here. 10 and 20, and then my object is here. So this is a reading that would be 13. For sure, this here could be 13 centimeters, but could also be 14 or maybe 12. Because what I can get out of example number 4 is that it is more than 10 and less than 20. So I'm certain about the tens, but I'm estimating the units. So these are my estimated digits. But when I come to this meter stick here, my certainty is a lot better than before. If we look at the first meter stick, my estimated digit is the decimal place. Okay? This is my estimated digit. And I'm using the same meter stick. And let's assume the same method of making the measurement. So I should have, on example 3, the same precision that I have in example 1. And the way to work this is to add a 0, 13.0. Notice that in measurements, we have that 13.0 is different than 13. Okay? When I write 13.0, I'm saying my estimated digit is the 0, is on the decimal place, and this is the kind of meter stick I'm using. When I write 13, I'm saying that my estimated digit is the 3, and I'm using a different kind of meter stick. So let's recap. We just saw that every measurement will have a number of digits that we are certain about them. We believe they're correct. And we just made an agreement to add one estimated digit. Well, these are called significant figures. And it becomes now for us a convention about how to write a measurement. We will always write as many correct digits we have, and then the last digit will be my estimated digit. In that sense, if I have a result, if someone measures something for me, as in, for example, 253.84 kilograms, I'm going to, if the person has reported this correctly, I'm going to assume that 253.8 are correct digits, and that 4 is going to be my estimated digit. Now, I would like you to consider what is expressed on this slide. A measurement is not a number. It is a range of acceptable values. Let me repeat this. A measurement is not a number. It is a range of acceptable values. Let's see what I mean by this. I'm going to start now sticking with the idea of meter sticks. This is a meter stick, what I'm representing, 10 centimeters, 11, 12, 13, 14 centimeters. But to save board, I am now just not representing the 0 through 10. But let's assume that this here is the 0 of my meter stick. So when I'm measuring something, remember we are going to compare, I need to put the beginning of my object in here, and let's say that it comes all the way through this point. So this is the object I'm trying to measure, and we are sticking with the simplest possible example. When I look at this, I think it's more than 12 and less than 13. So I'm going to write, for example, 12.4. So my result for now is 12.4 centimeters. But I need to put the meter stick by the edge of this thing, of my object I'm measuring the length. Well, maybe someone else would shift slightly to the left or slightly to the right, because you're just eyeballing what you think is the better thing. And let's remember, when we draw those things in the board, we draw them very nice and big and easy to see. But in reality, on a meter stick, it's not so easy to see this. And maybe I cannot properly touch what I'm measuring. I need to measure from a certain distance. Okay? Or maybe I'm measuring something that is moving. As if I drop a ball, the ball will fall, bounce back on the maximum height, and I try to see how high it goes. So this process of measuring would always include for us some uncertainty, and several people can get several different results. So I would say that anything, for example, between maybe this and this would end up being acceptable. Anything between these two results in here would be acceptable. And this exactly is what I'm saying, that the measurement is not exactly a number, but rather a range of possibilities. Now, how do we learn how to express this range of possibilities, how big it is? That's an issue for future lessons. I just need you to understand the concept of the range. And how do we then express this? We would do what we call the margin of error. So let's just pretend, for the sake of the argument, that my range of possibilities can go from somewhere between 12.1 to 12.6. 7, just to make it easier, initial example. So my range has a 0.6 centimeters length. I believe the best reading is 12.4, but anything between 12.1 and 12.7 is fair game, is right for me, is acceptable. And therefore, I can actually express this length as 12.4 plus or minus 0.3 centimeters. So I'm telling you, I believe that 12.4 is the best measurement, but anything between 12.4 minus 0.3 or 12.4 plus 0.3 is fair game, is acceptable. Again, how did I get these limits and this range? At this point, I just made it up. In future lessons, we're going to then learn a little bit more about how to get that. Now let's talk about the possibility of overlapping margins of errors. And one example that always comes to my mind when we talk about this is surveys about intention of voting for a given candidate, or sometimes the surveys about what people think about some effects, about a movie, whatever. Let's stick with election. So sometimes you hear this here. Candidate A has 42% of the intentional vote. Candidate B has 45% of the intentional votes. That's a technical match. What does it mean, this? Well, one piece of information that is not always told in the TV is the margin of error. So let's say that in this example, my margin of error is plus or minus 3 points. So I just say candidate A, I said, has 42%. Candidate B has a 45%. But now I'm telling you guys that the margin of error is to be considered to be plus or minus 3 points. So plus or minus 3%, and then plus or minus 3%. I'm actually now going to color code this. So candidate A, I'm going to represent in pink here, or whatever color is this. So when I say 42 plus or minus 3, what I'm saying is I believe candidate A will get 42% of the vote, but anything between 39 and 45 is okay. It's fair game, and I can claim I was right. When I say that candidate B will get 45 plus or minus 3%, I say that I expect candidate B to get 45, but anything between 48 and 42 is fair game, is also acceptable for a possible outcome. Now you see that there is an overlap between these two margins of error. And if there is an overlap, in reality, I cannot predict the winner, because we just might as well have candidate B coming out with 43% and candidate A coming out with 44%, and A would be the winner. Yes, I know that as it looks like, B is more likely to win, but they are technically speaking matched. So anytime we take a measurement or we calculate something in physics or in science, and we have an overlap of the margin of error, we can say that the results are in agreement. I'm not going to say they are equal, but they are in agreement. I cannot distinguish them. One thing also that I want to point is that in these static examples that we're discussing here, we always get the impression that the only thing that matters in the measuring process is just the precision of the instrument and my eyeball placing it. Like I mentioned before, if I can place my meter stick right against what I'm measuring, I'm going to get one quality, one precision. The same meter stick, the same object, but somehow I need to place it farther away, I get a different result. If this object is moving as I'm trying to measure, it's going to be even harder. So the precision and the margin of error of my measurement is determined not only by the instrument itself, but also by how the measurement is performed, by how I'm doing my lab.